U.S. Physics Olympiad Year 2024 F = MA. This year, as usual, 75 minutes were given for 25 problems. If you want to stay up to date with interesting Olympiad problems, subscribe to this channel. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com. Problem number 1. An archer fires an arrow from the ground so that it passes through two hoops, which are both a height h, above the ground. The arrow passes through the first hoop 1 second after the arrow is launched, and, through the second hoop another second later. What is the value of h? Problem number 2. An amusement park ride consists of a circular, horizontal room. A rider leans against its frictionless outer walls, which are angled back at 30 degrees with respect to the vertical, so that the rider's center of mass is 5.0 meters from the center of the room. When the room begins to spin about its center, at what angular velocity will the rider's feet first lift off the floor? Problem number 3. A simple bridge is made of 5 thin rods rigidly connected at 4 vertices. The ground is frictionless, so that it can only exert vertical normal forces at B and D. The weight of the bridge is negligible, but a person stands at its middle, exerting a downward force F at vertex C. In static equilibrium, each rod can be experiencing either tension or compression. Which of the following is true? Answer: A. Only the vertical rod is in tension. Answer: B. Only the horizontal rods are in tension. Answer: C. Both the vertical rod and the diagonal rods are in tension. Answer D. Both the vertical rod and the horizontal rods are in tension. Answer E. All of the rods are in tension. Problem number 4. A bouncy ball is thrown vertically upward from the ground. Air resistance is negligible, and the ball's collisions with the ground are perfectly elastic. Which of the following shows the kinetic energy of the ball as a function of time? Assume the collisions are too quick for their duration to be seen in the plot. Problem number 5. A massless inclined plane with angle 30 degrees to the horizontal is fixed to a scale. A block of mass m is released from the top of the plane, which is frictionless. As the block slides down the plane, what is the reading on the scale? Problem number 6. A pendulum is made with a string and a bucket full of water. When the string is vertical, the bottom of the bucket is near the ground. Then, the pendulum is set swinging with a small amplitude, and a very small hole is opened at the bottom of the bucket, which leaks water at a constant rate. After a few full swings, which of the following best shows the amount of water that has landed on the ground as a function of position? Problem number 7. A particle travels in a straight line. Its velocity as a function of time is shown below. Which of the following shows the velocity as a function of distance x from its initial position? Problem number 8. A rod of length L is sliding down a frictionless wall. When the rod makes an angle of 45 degrees to the horizontal, the bottom of the rod has speed v. At this moment, what is the speed of the middle of the rod? Problem number 9. When a car's brakes are fully engaged, it takes 100 meters to stop on a dry road, which has coefficient of kinetic friction μk equals 0.8 with the tires. Now suppose only the first 50 meters of the road is dry, and the rest is covered with ice, with μk equals 0.2. What total distance does the car need to stop? Problem number 10. A block of mass m is connected to the walls of a frictionless box by two massless springs with relaxed lengths L and 2L, and spring constants key and 2 key respectively. The length of the box is 3L. The system rotates with a constant angular velocity omega about one of its walls. Suppose the block stays at a constant distance r from the axis of rotation, without touching either of the walls. What is the value of r? Problem number 11. Two hemispherical shells can be pressed together to form an airtight sphere of radius 40 centimeters. Suppose the shells are pressed together at a high altitude, where the air pressure is half its value at sea level. The sphere is then returned to sea level, where the air pressure is 10⁵ pascals. What force F, applied directly, outward to each hemisphere, is required to pull them apart? Problem number 12. A space probe with mass m at point P traverses through a cluster of 3 asteroids, at points A, B, and C. The masses and locations of the asteroids are shown below. What is the torque on the probe about point C? Problem number 13. Two frictionless blocks of mass m are connected by a massless string which passes through a fixed massless pulley, which is a height h above the ground. Suppose the blocks are initially held with horizontal separation x, and the length of the string is chosen so that the right block hangs in the air as shown. If the blocks are released, the tension in the string immediately afterward will be T. Which of the following shows a plot of T versus x? Problem number 14. A bead of mass m can slide frictionlessly on a vertical circular wire hoop of radius 20 centimeters. The hoop is attached to a stand of mass m, which can slide frictionlessly on the ground. Initially, the bead is at the bottom of the hoop, the stand is at rest, and the bead has velocity 2 meters per second to the right. At some point, the bead will stop moving with respect to the hoop. At that moment, through what angle along the hoop has the bead traveled? Problem number 15. The viscous force between two plates of area A, with relative speed v and separation d, is F equals eta AV over d, where eta is the viscosity. In fluid mechanics, the Ohn-Zorge number is a dimensionless number proportional to eta, which characterizes the importance of viscous forces in a drop of fluid of density ρ, surface tension, gamma, and length scale L. Which of the following could be the definition of the Ohn-Zorge number? Problem number 16. A child of mass m holds onto the end of a massless rope of length L, which is attached to a pivot at height h above the ground. The child is released from rest when the rope is straight and horizontal. At some point, the child lets go of the rope, flies through the air, and lands on the ground a horizontal distance d from the pivot. On Earth, the maximum possible value of d is dE. If the setup is moved to the Moon, which has 1/6 the gravitational acceleration, what is the new maximum possible value of d? Problem number 17. Consider the following system of massless and frictionless pulleys, ropes, and springs. Initially, a block of mass m is attached to the end of a rope, and the system is in equilibrium. Next, the block is doubled in mass, and the system is allowed to come to equilibrium again. During the transition between these equilibria, how far does the end of the rope, where the block is suspended, move? Problem number 18. A satellite is initially in a circular orbit of radius r around a planet of mass m. It fires its rockets to instantaneously increase its speed by delta v, keeping the direction of its velocity the same, so that it enters an elliptical orbit whose maximum distance from the planet is 2r. What is the value of delta V? Hint: when the satellite is in an elliptical orbit with semi-major axis A, its total energy per unit mass is negative gm/2a. Problem number 19. A wheel of radius r has a thin rim and 4 spokes, each of which have uniform density. The entire rim has mass m, 3 of the spokes each have mass m, and the 4th spoke has mass 3m. The wheel is suspended on a horizontal frictionless axle passing through its center. If the wheel is slightly rotated from its equilibrium position, what is the angular frequency of small oscillations? Problem number 20. Four massless rigid rods are connected into a quadrilateral by 4 hinges. The hinges have mass m, and allow the rods to freely rotate. A spring of spring constant K is connected across each of the diagonals, so that the springs are at their relaxed length when the rods form a square. Assume the springs do not interfere with each other. If the square is slightly compressed along one of its diagonals, its shape will oscillate over time. What is the period of these oscillations? Problem number 21. A syringe is filled with water of density ρ and negligible viscosity. Its body is a cylinder of cross-sectional area A1, which gradually tapers into a needle with cross-sectional area A2 much less than A1. The syringe is held in place and its end is slowly pushed inward by a force F, so that it moves with constant speed V. Water shoots straight out of the needle's tip. What is the approximate value of F? Problem number 22. A spherical shell is made from a thin sheet of material with a mass per area of sigma. Consider 2 points, P1 and P2, which are close to each other, but just inside and outside the sphere, respectively. If the accelerations due to gravity at these points are g1 and g2, respectively, what is the value of absolute value of g1 minus g2? Problem number 23. Collisions between ping-pong balls and paddles are not perfectly elastic. Suppose that if a player holds a paddle still and drops a ball on top of it from any height h, it will bounce back up to height h/2. To keep the ball bouncing steadily, the player moves the paddle up and down, so that it is moving upward, with speed 1 meter per second whenever the ball hits it. What is the height to which the ball is bouncing? Problem number 24. When a projectile falls through a fluid, it experiences a drag force proportional to the product of its cross-sectional area, the fluid density ρf, and the square of its speed. Suppose a sphere of density ρs much greater ρf, of radius r is dropped in the fluid from rest. When the projectile has reached half of its terminal velocity, which of the following is its displacement proportional to? Problem number 25. A yo-yo consists of 2 massive uniform disks of radius r connected by a thin axle. A thick string is wrapped many times around the axle, so that the end of the string is initially a distance r from the axle, then, the end of the string is held in place and the yo-yo is dropped from rest. Assume that energy losses are negligible, and that the string has negligible mass and always remains vertical. Below, we show a cross-section of the yo-yo partway through its descent, between the moment the yo-yo is released and the moment the string completely unwinds. Which of the following is true regarding the yo-yo's acceleration? Answer: A. It is always 0. Answer: B. It points downward, but decreases in magnitude over time. Answer: C. It points downward and has constant magnitude. Answer, D. It points downward, but increases in magnitude over time. Answer E. None of the above.